simulation and simulation workflow, how to set up a simulation run, the definition of water flooding or water injection development strategy, and then the definition of surfactant flooding and its application in reservoir simulation, and then the effects or modifications on the surfactant simulation model. At the end we have a case study to compare between simulation results. So next is the simulation model construction, and finally the sensitivity run and simulation results. So as an background and permanent overview, I already start with, which is the reservoir engineering. Typically, it's a discipline of petroleum engineering that's concerned with the applications of fluid flow in the porous media and the subsurface reservoir, as you can see in this 3D layout. So in the porous spaces, as you can see, we have in the a perspective of reservoir. As you can see, we have rock grains or rock matrix, and between we have porous spaces. In the porous spaces, as you can see, we have the reservoir fluid itself. So this is the process of fluid flow in the porous media. Therefore, applications, the main fundamentals of reservoir engineering are typically the Darcy's law, because we have fluid flow in a porous media. So Darcy's law or flow rate equation will be used to characterize the fluid flow or flow rate in the porous media. Second fundamental, which is the material balance or continuity equation, because we have a specific subsurface volume or specific storage for such a reservoir. So the remaining volume at any time throughout the reservoir lifetime is the initial volume minus the produced volume. The last basic of reservoir engineering, which is the BVT or equation of a state model, because the fluid properties like oil density, oil viscosity, oil formation volume factor, etc., are a function of pressure. So at any time, the equation of a state or BVT model will be used to characterize fluid parameters against at any value of pressure, starting from average reservoir pressure to the bottom hole flowing pressure, and then wellhead pressure, and finally the terminal pressure at the end of the production system. This is simply the entire perspective of the petroleum reservoirs, from the porous media to the surface connection and surface network to the transportation pipelines and so on. So this is the oil field operations, oil field development operations. Specifically, we have this typical performance against the cash flow. We have 4 different phases or development periods in the oil field. Starting with the exploration phase, which means we have a specific understanding. Still, we acquire data from the subsurface, and we have negative cash flow due to the capital cost invested in the concession acquisition and seismic processing and so on. Next, which is the delineation phase. In this phase, we have a successful discovery, and then we have the production build-up, followed by the discovery of successful assets. And the next phase, which is the development phase. In this phase, the reservoir is highly understood. We in this phase we have the maximum or peak oil production, and finally the maturity phase. And as you can see, we have a start of production decline due to the reduction of reservoir energy in terms of reservoir pressure due to production. So, and the reservoir simulation generally or reservoir management plays a very important role to manage the reservoir development and set the optimum development strategy in terms of the ultimate oil recovery to so in this example we have three different depletion or development scenarios. This is can be applied using a simulation model, and you can set the most economic model in terms of field operation and the development strategy. So field development planning is typically follows the same behavior. This is the exploration phase, start production buildup. So typically we have three types of or three periods in the oil recovery. The primary recovery, which means we have the natural energy of reservoir using natural flow artificial lift. Secondary recovery, and then the tertiary recovery. So as you can see, we have incremental oil recovered within every phase in terms of secondary and tertiary recovery techniques. So to highlight the comparison between the oil recovery techniques, basically the primary recovery, we have plus or minus 20% of the original oil in place, which is recovered. Typically, we have natural flow, artificial lift, any artificial lift system in the wells. The improved oil recovery techniques, we have secondary and tertiary recovery technique. For secondary recovery, basically we have the immiscible displacement process like water injection or pressure maintenance and gas injection. And finally, the tertiary or enhanced oil recovery techniques. We have four basic categories, including thermal, gas injection, chemical, and other techniques. Our techniques of interest in this webinar are the water injection or water flooding as a secondary recovery technique against the enhanced oil recovery technique using a chemical injection or specifically surfactant flooding. So this is the simply the oil recovery techniques. So to highlight the incremental oil recovery due to such secondary or tertiary recovery techniques, this is the this relationship between oil recovery and as a percentage of the original oil in place against time using three different recovery techniques. This is the traditional water flooding as a secondary recovery against the polymer flooding, which is a technique in a chemical enhanced oil recovery technique to control the mobility ratio and decrease the mobility of water, and accordingly will increase the mobility of the residual oil or the remaining oil. And then this is the surfactant polymer flooding, which is shows the highest achieved oil recovery. So surfactant is one of the important enhanced oil recovery technique, can be associated with other techniques like polymer or even alkaline and so on. So this is the regarding reservoir simulation. This is the simply the philosophy of simulation. We have several reservoir realizations in terms of all subsurface data, like the reservoir description, fluid and rock properties, the saturation functions, relative mobility data, aquifer data, and force or reservoir structure, subsurface horizons, and the fluid contacts, and so on, and the fishes distribution. All of these data will be integrated together to get a specific reservoir realization or static model. And then we have to apply specific development strategy in terms of a number of wells that will be drilled, the other constraints in the production system, and the surface facility, and so on. And finally, we have a certain simulation case. So a simulation case is an integration between specific reservoir realization and development strategy. So a reservoir characterization is a critical process in such reservoir management or reservoir simulation. So all of this data are important. Petrophysical analysis of well logs, petrology or mineralogy, rock units and from core data, relative minerability data, and capillary pressure data. All of this data must be defined to start dynamic modeling phase to get a specific simulation, 3D simulation model. So simulation simply, we have discretization, which means we subdivide the reservoir into specific rock units or grid cells or grid blocks, as you can see. So this is the discretization in space, and to solve, and we assume build a specific partial differential equation or simulation equation in terms of the pressures and saturations. And then we will solve, the simulator will solve the partial differential equations for a specific time step. So we have discretization in space due to subdivision of the reservoir into grid cells or grid blocks, and discretization in time because we will solve the simulation equation across a specific time step. So basic equations or basic fundamentals for like any reservoir engineering application are Darcy's law, equation of a state, and continuity equation. So a simulator will solve the a set of complex nonlinear system of equations and get the pressures and saturation for every grid block or grid cell. So this is simply the simulator like Eclipse simulator or other simulators. We have specific sections or specific models. So reservoir grid model or geometry and properties, we will calculate both volumes and transmissibilities. For properties, specifically fluid and rock properties, we have the simulator will calculate initial fluid saturations and pressures and in-place volumes. The data from the development strategy, typically well data and production data or historical production completion data and so on, will be used to assign the development strategy and predict the reservoir performance under specific depletion scenario. So this is the simply the flow simulation. We have fluid flow from every one grid block to the next grid block, like these grid blocks. A flow from the grid block to the well completion at the grid cells. We have wells, because at these locations we have wells, and the flow within the wells itself, and then to flow in the surface network. This is simply simulation flow equations. It's a function of transmissibility and mobility and potential difference. So BVT and scale data are important and critical in dynamic modeling. So BVT data, as you can see, are important to characterize fluid properties, while production as a function of pressure, and important to apply the mass balance equation. And also BVT data will be used to convert the reservoir volumes to equivalent mass to apply the mass balance equation. And for scale data like relative mobility data and capillary pressure, they will be used to assign or define the transition zone between the oil and water, and set the minimum and maximum saturation for every phase in the reservoir, and also scale data will control the relative mobility of every phase in the presence of other phase, or in other words, the relative mobility curve. So Eclipse, the mechanism of Eclipse, we have the specific sections in the Eclipse or simulation data file. So the simulator will make processing and check consistency of this data. So we have two important sections, which are the run spec section and schedule section that control time-dependent data. So back to simulation flow equation, as you can see. So this is the equivalent simulation data file section. For transmissibility, it's a function of geometry and or 3D rock geometry and rock properties. So the equivalent data section in simulation data file is grid section and edit section. For mobility, it's typically K over du function of fluid properties. So we will find this in the props region and solution section. And for potential difference or production data, they are available in the schedule section. So this is the back to the mechanism of Eclipse. We have geological model or 3D grid. So data from grid and the edit sections will be used to calculate volume and transmissibility. For probe section, simply the fluid and scale data in this relationship, as you can see, fluid contacts and the BVT and scale data. Simulator will make initialization to define initial pressures and saturation and in-place volumes. For the well operations, as you can see, it's a function of completion data and the production data. So data will be available in the schedule section. So simulator will define wells and surface facility and define production constraints. So as to set up a simulation run, simply we have development strategy. Development strategy is used to define or specify times to be simulator, the start and end time for the simulation run, and also will define the well operations or the depletion strategy to be applied in the field. So development strategy, we have two different modes: the history matching or history strategy. In this case, we will import the historical production data and the actual facility and production constraints, or even production or injection data, and I fine-tune or adjust the 3D model. In other words, to calibrate your model. Once your model is calibrated in the history strategy or in the history matching phase, so the next model is the prediction strategy. In this case, we will specify defined unlimited number of depletion strategies and predict the reservoir, the equivalent reservoir performance. So this is the simulation run. As mentioned, this is the development strategy. Will define dates, will our group of wells, well rates or construction constraints. And for the next step is to define a simulation case. And in this step, we have to select a specific 3D grid, define the pivots, and select the simulator. So setting up a simulation has simply you have all of these components. The first, which is the grid, and the 3D grid and the corresponding parameters and corresponding pivots like porosity and permeability in 3 directions, permeability in X and Y and Z direction. Next, which is functions. functions in a simulation means the fluid and fluid functions or fluid parameters and scale parameters. As you can see, we have the BVT parameters against the pressure and scale parameters against water saturation. And for initial conditions, we have to define fluid contacts, oil and gas, oil water contact and gas oil contact. For strategies as defined before, it's maybe history or prediction strategy, and then you can assign and control the outputs of simulation and a type of required simulation results. And therefore, we have advanced options to control the simulation running time, and other features can be defined. So this is a snapshot of how to define a simulation case in this window. As you can see, we have different tabs related to different data required. The first tab, which is the most important, or the grid tab, we will define the minimum data required in this tab, which is the 3D grid parameters, specifically porosity and directional.
Hisham. Hisham. Hello, can you hear me? Please, everyone, don't forget to fill this feedback form. This is the feedback form for this one. Please, everyone, don't hesitate to fill this form so you can always fulfill your needs. Okay, thank you so much. I don't know. I'm trying to reach Engineer Hisham. Maybe have some connection problem. To let him for a moment.
Yes,
Hello,
I'm
Hisham,
sorry
and
for
welcome
this.
back.
Hello, can you hear me?
Yes.
Yes,
Welcome
sorry
back.
for this technical problem. But anyway, we will continue. So as mentioned,
Can you share your screen, please?
yes. Homogeneous reservoir structure, high porosity, high permeability, no water sensitive clays to avoid water compatibility issues. It's preferred for water wet reservoirs, high transmissibility between the flanks of reservoir in case of the peripheral injection, low oil viscosity, low oil density, and so on, thick oil volume. All of these parameters are ideal or recommended for successful water flooding or water injection projects. So this is the a comparison of simulation results of this. We have about 19% recovery factor using the volumetric depletion or depletion strategy against up to 30% recovery factor using the water flooding. This is the just sensitivity runs on the injection on the water injection rates. So additionally to water flooding, water injection, what is the surfactant flooding? Surfactant, it's simply it's a tertiary or enhanced oil recovery technique. In this technique, we will add or a small amount of surfactant, typically from 0.3 up to 1 volume percent will be added to the liquid or aqueous phase injected into the reservoir. So it's simply we have this is the surfactant injection well, and this is the oil bank surfactant, and this is the mobile zone of residual oil, and surfactant will be injected right here. So the mechanism of surfactant, as you know, is to reduce the interfacial tension between the oil and water and the residual oil in the reservoir, and accordingly the surfactant may change or may modify the reservoir waterability from the oil wet to a water wet case. So process description in details. This is the process of surfactant flooding. As mentioned, we have this water drive, and this is the oil bank and surfactant. We may have additional polymer to control the mobility ratio and decrease the mobility of water. So behind the flowing oil bank, we have some oil trapped or residual oil, which is we can call it as the capillary trapped residual oil. This capillary trapped residual oil can be recovered using surfactant flooding by the process of desaturation, because the surfactant flooding is simply reducing the oil water interfacial tension. So the remaining or the capillary trapped residual oil will can be recovered. So this is simply due to a strong reduction in the oil water interfacial tension. So so as a planning of the such enhanced oil recovery technique, we have basic steps, including reservoir characterization and model construction and history matching. Next, it's just the oil EOR visibility study or screening study or lab experiment on the core samples, then pilot test. So applying the field on a small scale. And next we field operation on the field application on a large scale, different wells and the corresponding injection pattern and so on. And finally, the project summary in terms of the economic results and comparison between different scenarios. So now I need to define a very important term in such water injection or even water flooding or surfactant flooding, which is the voidage replacement. Voidage replacement, it's or voidage replacement ratio. It's the injection to production ratio on a specific field wide or a pattern. So reservoir volume, it's simply the reservoir voidage. It's the produced oil and water and even the free gas production measured at the reservoir conditions. So we have to convert the free gas production to equivalent liquid production. Voidage replacement is an important parameter to manage water flooding projects. So the target for the majority of water flooding projects is to achieve a voidage replacement ratio more or less 1. It's recommended to be higher than 1. So voidage replacement ratio, it's the summation of water injection plus any water influx due to water aquifer and so on, divided by the reservoir voidage measured at reservoir conditions. It can be defined as fluid in, fluid out, or injection withdrawal ratio. So based on the monthly production and the injection data, so this is the definition of reservoir voidage. It's simply the total production from the reservoir oil and water and the free gas production converted to reservoir conditions, because we have the formation volume factors for oil and water and gas. And accordingly, this is the voidage replacement ratio. It's a summation of water injection divided by the reservoir voidage. So to keep or to maintain the average reservoir pressure is at high level, or even to increase the average reservoir pressure, it's important to keep the voidage replacement ratio higher than or equal to 1. So water flooding strategy in drill, it's this is the development strategy or water flood strategy. We have several rules to control water flooding. This is the reporting frequency, which is the frequency of simulation reporting of the simulation results, and this is, it can be assigned based on the required frequency of the results. The second important rule, which is group rate production control, this rule in reservoir simulation will be used to control the group of wells or the production wells, and assign the corresponding production control. So as you can see, this is group rate production control as highlighted right here. We have a group of wells, and then can define a specific oil rate, and this is a target rate, and actions to be taken in this target is not achieved like this. We will not go through on details in this process, but just it's an overview. So next, which is well production, well pressure production control. This rule is will be used to control the production wells by applying specific minimum limit for the bottom hole pressure, like this. This is the group of wells for the producers in this model. Control model is the bottom hole pressure, and this is the applied minimum bottom hole pressure using this well pressure production control. So, water injection control, as the name implies, this rule will be used to control the water injection wells. So, the self control mode for water injectors is typically from surface control, because we can control the injectors from surface to control water injection rate and the injection pressures and so on, and assign the required injection rate. And last important rule, which is group voidage replacement injection. So this rule, as its name implies, controls the injection to replace production voidage. It's simply the voidage replacement ratio. So in this example, we have a group of wells, which is injectors, and the phase, the injected phase, which is water, and the voidage replacement fraction is 0.95. It can be higher than 1. It's to keep the reservoir pressure at higher levels in case of the required criteria is to achieve high voidage replacement ratio. So so now I will highlight the surfactant modeling, surfactant flooding. So simply in simulation, just to highlight an quick overview, we have fundamental equations like any other applications, continuity, flow rate of Darcy, and BVT model or BVT or equation of state. They are the fundamentals for simulation equations. Simulator will we will combine all of these principles to set simulation equations for every grid block or grid cell in the 3D simulation model, and then the simulator will solve the partial differential equation to get the pressure, water saturation, and gas saturation for every grid block. This partial differential equations will be solved using different approaches or different techniques. But it's important to know, just to highlight, we have a nonlinear set of equations, and the unknowns are pressures, water saturation, and gas saturation. So for surfactant model in Eclipse 100, actually the distribution of the injected surfactant will be considered as a function of the water phase. So a simulator will solve a conservation equation for surfactant within the water phase, and simulator will be use the fully implicit approach. Fully implicit simply is a simulation as an approach to solve simulation equations at for pressures and saturation at the end of the time step, because in simulation we have specific time steps, and simulator will solve equations per single time step and so on. So we'll highlight some keywords related to the surfactant model, but you have to keep in mind this is the material balance equation, net rate of flow in equal rate of accumulation plus production. This is simply if we have this grid block, this is the pore volume of this grid block. It's simply the directions dx, dy, dz. It's very simple, multiplied by porosity. So we have the pore volume. So oil in place, it's according to this simple equation. So a rate of accumulation of oil during a single time step, it's the difference between the oil in place at the n+1, which is the time step at the end of time step, minus the oil in place at the beginning or start of time step, multiplied by a specific time step, or delta t. It's a very simple presentation of simulation equations. So this is the black oil simulation, very simple as defined before. Just to keep in mind, this term is oil flow equation, and we have the pressure in the on the left-hand side of this equation. So we have three different equations for oil, water, and gas phases according to the material balance concept. It's very simple. So just to keep in mind, we have such modifications in the black oil model in case of surfactant flooding. So for water phase continuity equation, we have this term to assign for gravity effects. For brine continuity equation, we have this term to consider the salt saturation in the brine, and we have surfactant continuity equation, and we have it's a function of surfactant concentration in the water phase and surfactant adsorption term. This term is simply because the injected surfactant, some of the injected surfactant may be lost on the surface of pore spaces. So this term will be considered in the surfactant continuity equation. So in surfactant flooding, simply the surfactant will be injected into water phase and represent additional component in the system. So we have oil, water, gas, and surfactant. So this is the terminology of the last equation, just for your reference. So simulation method of solving surfactant flooding, we have fully implicit approach, and method of and this is the results for every for surfactant flooding model. We have for every grid block 5 unknowns, which means pressure, water saturation, gas saturation. This is simply the basic unknowns. We have 2 additional unknowns, which are surfactant concentration and salt concentration in the brine. So we have 5 equations and 5 independent unknowns. So this is we have the 5 equations we have to solve for oil, gas, and water, and equation for surfactant, and equation for the brine. And this is the all unknowns we have. So surfactant model, the surfactant, we have surfactant reservoir brine and injected water. They are represented as miscible component in the aqueous phase. And surfactant absorption, as mentioned, it's a term, amount of surfactant will be lost in the surface of the pore spaces, and this is the term of the absorption. So surfactant effects, as mentioned, surfactant will modify 3 different parameters in the simulation model, modify BVT water properties, modify scale data in terms of the oil water surface tension, and accordingly surfactant will decrease the capillary pressure, and also it will change the rock wettability due to the adsorbed surfactant on the rock surface. So simply we have several keywords in the simulation data file. Just to keep in mind, we have these keywords. You can back to the reference for the simulator to get more information regarding these keywords. But what's important to know, this is the viscosity of water surfactant solution. It's a function of pressure and surfactant the surfactant concentration. This term C capital, just this is the simply the viscosity of water surfactant solution. So in Eclipse data file, we have this keyword serve this, which is surfactant viscosity. And in this keyword, this is BVTW, which is BVT of water. This value is the water viscosity. But back to this keyword, which is surfactant viscosity, it's equal the viscosity of water at 0% surfactant concentration. But at 30, surfactant concentration is 30, so this is the corresponding viscosity of this solution. Changes in relative permeability, as mentioned, because surfactant will reduce all water interfacial tension. Additionally, surfactant will decrease the capillary pressure. So we will simulate this process by using the capillary number. The capillary number is a term will control the miscibility of surfactant with the formation water and injected water. So we have this keyword which is controls the capillary number. This is the interpolation parameter to control the capillary number in the surfactant model. So back to relative permeability in this model. So relative permeability, it's a function between miscible and immiscible relative permeability curve. This is the immiscible curve, and this is the miscible curve. So at a specific saturation, so the simulator will calculate the final relative permeability based on the interpolation between immiscible and miscible relative permeability curve. So the final relative permeability, according to this equation, is a function of the interpolation parameter or weighting average F multiplied by relative permeability of the oil with relative permeability and water with relative permeability. This is simply the modifications in relative permeability model. Next, for water saturation, because surfactant will typically reduce the capillary thread residual oil saturation. So this is simply the oil water capillary pressure, as you know, this equation. But in this model, we have just modification in this equation. This is we have this multiplier. This multiplier is simply a function of surfactant concentration multiplied by the original capillary pressure equation. So this keyword, which is surfactant interfacial tension against the surfactant concentration. So as you can see, as long as we have high surfactant concentration, so in the left hand side, so the surfactant, the surface tension or surfactant interfacial tension will be reduced like this. Last is this the process of desaturation or capillary desaturation. It simply means the reduction of capillary trapped residual oil. So we have this term, which is capillary number. I won't go through in details, but we have simply we have this equation, which is capillary number. It's important to know we have this relationship, which is against the residual non-wetting phase residual oil saturation against capillary number. So as long as the capillary number is increasing, the residual oil saturation is decreasing, as you can see. So this is the range of normal water flooding. We have high residual oil, but with surfactant flooding, we have a reduction in the capillary or increase in the capillary number. Accordingly, as you can see, we will have a reduction in the residual oil saturation, which is the objective of of surfactant flooding, is to increase the capillary number. Accordingly, reduce the residual oil saturation and increase oil recovery. So this is a relationship between oil recovery and the capillary number. As you can see, it's uh, once we have increasing capillary number, the oil recovered will be increased. Last to consider, it's a surfactant absorption. It's amount of surfactant lost in the surface of the rock. For surfactant flooding best practices, it's important to use a pre-flush with different chemicals to avoid a loss of surfactant on the rock surface. So in simulator, we have this keyword just to define the surfactant absorption against surfactant concentration. And last parameter, which is the wettability change. As mentioned, surfactant will change the wettability or modify the wettability of the rock based on surfactant concentration according to this equation. So this is the Eclipse 100 keywords used in surfactant model in different sections. I will not go through in more details. In this case study, we have, this is the model description. We have a model of 300 grid blocks, and this is the area, berm X, berm Y, and berm Z. Porosity is 0.25. Water viscosity 0.34 centibars, oil viscosity is 0.47, and this is the initial reservoir pressure 270 bar, and this is the start of simulation run. It's at 1st of May 1990. We have single producer and single injector. So this is the model description of this is the permeability in X direction, distribution, berm in Z direction, water saturation, and porosity distribution. So we have several sensitivity run in this model to compare between water flooding against surfactant flooding, sensitivity on surfactant viscosity, surfactant concentration and absorption, capillary desaturation, and other, and we will display simulation results. So this is the we have this is base this is a case. We have water injection from the second day of production. In this case, the surfactant flooding is started at the after 160 days of beginning of water injection. While the second case, we have only water flooding with the specific parameters like this. So as the comparison between water flooding against surfactant flooding, so in the blue color, this is the behavior or the performance of water flooding. As you can see, for oil production rate, this is the we have more reduction in water flooding at this time, while for surfactant flooding, we have additional oil increase in oil production after start of surfactant flooding. For water cut, as you can see, we have a reduction in the field water cut due to surfactant flooding, because surfactants will decrease the residual oil saturation and accordingly increase the oil recovery. For field cumulative oil production cumulative, so as you can see, we have this is an incremental recovery due to surfactant flooding, and this is the reduction in cumulative water production for the surfactant model. This is the cumulative production. We have 75, about 75 million stock tank barrel against 61 million for the traditional water flooding. So we have about 14 million stock tank barrel incremental recovery due to surfactant flooding. So for water saturation, as you can see, this is the comparison between the two cases. So in case one, this is the injector and this is the equation of producer, and the grid cells are around the injection well. So we have this is the color scale of water saturation. So grid cells in the in colors near to the red color, we have zero water saturation or low water saturation, and the blue color we have about 100% water saturation. So for the surfactant model, we have in the grid cells around the injector, we have about 100% water saturation, which means the low residual oil saturation, or which is SORW, against in the traditional water flooding projects. This is the we have about 65% residual water saturation, 65% water saturation in these grid cells, which means we have about 35% residual oil saturation still in the reservoir can be recovered. So for this is the effect of surfactant viscosity, as you can see. We have three different scenarios. In the red color, we have the lowest viscosity. Against in the green color, we have the highest surfactant viscosity. So the simulation results shows the decreasing surfactant viscosity means the decrease in the viscosity of surfactant water mixture, and then it will accelerate the flow of the mixture, and this will create a small reduction in the oil rate and increase in the water cut. Increase in the in terms of oil production rate, and increase in the oil the viscosity of surfactant is better in terms of cumulative production or oil production rate. This is the water saturation at different viscosity, surfactant viscosity. So this is the high surfactant viscosity shows the a clear transition between the grid cells of 100% water saturation and grid cells of residual oil saturation. So increasing surfactant viscosity will improve the displacement process and reduce the residual oil saturation. So this is the effect of surfactant concentration. As you can see, we have three different cases. In the green color, we have the highest surfactant concentration. So increasing the concentration of surfactant will increase the recovery factor and increase the corresponding oil production, and accordingly reduce the water cut and cumulative water production. So for residual oil saturation, as you can see, this is the we have for the highest surfactant concentration, we have the best simulation results. This is the grid cells of about zero residual oil saturation, which means we have better recovery, or highest achieved recovery in terms of oil production and cumulative oil production rate and oil production cumulative. So the effect of surfactant absorption, as mentioned, it's amount of surfactant lost in the surface of both in the rock surface. So high surfactant absorption, that means we have in this model, in this scenario, in the black color, we have a reduction in the reduced effect of surfactant, because amount of surfactant is lost in the rock surface. So the corresponding oil saturation or the cumulative oil production is lower. And this is the effect of surfactant absorption on the residual oil saturation. It's better to have low absorption term of surfactant. The last effect, which is the capillary desaturation. So this is we have three different scenarios. So if we had achieved 100% miscibility between surfactant and the formation water, you will achieve the highest oil production rate and highest oil production cumulative, and accordingly the lowest water production cumulative, and so on. And this is in terms of residual oil saturation. So high full miscibility means we have very low residual oil saturation. Against 0.1 miscibility, we have these great cells in the blue color. We have high residual oil saturation. So this is the summary of results, and this is the conclusions of this webinar. So Eclipse 100 models the distribution of surfactant within the water phase. The Eclipse 100 doesn't provide detailed chemical simulation of surfactant flooding, and the surfactant flooding is one of the enhanced oil recovery technique, must be applied under the correct and appropriate reservoir conditions, and simulation results must be approved or calibrated by a correct and history matching. High absorption levels of surfactant, that means that affect the surfactant flooding performance. Surfactant concentration is the most effective parameter on the field performance in terms of cumulative production and production rates. That's all I have actually in this webinar, and thank you so much for joining me in this session. And it's time, if you have any questions, any comments, please go ahead.
Thank you so much, Engineer Sham, for this outstanding session. So please, if anyone has any question, you can please type it in the chat, and Engineer Sham can reply to all your questions. And also don't forget that I shared with you a feedback form for this session, so please make sure everyone to fill it. You are welcome, Ramon. So does anyone else has any question, please? Don't hesitate to ask. Can you please explain the effect of surfactant on capillary pressure?
Okay, Jad, can okay, let me check the question myself. It's
Okay, of
I
course.
think please explain the effect of surfactant on capillary pressure and its relationship. Actually, the main mechanism of surfactant is to reduce the oil water interfacial tension to very low levels. Accordingly, the surfactant will reduce the capillary trapped residual oil saturation, Accordingly, it will reduce the capillary pressure in this pore spaces. So the residual oil or the oil left in the reservoir in these pore spaces due to the high capillary pressure can be recovered. So the better surfactant flooding will reduce the capillary pressure, will reduce oil water interfacial tension. Accordingly, it will increase the oil recovered by recovering the capillary trapped residual oil. Its relationship we have, as mentioned, we have simulation equation in terms of the capillary number. This capillary number is will control the value of capillary pressure against surfactant concentration. So at a specific surfactant concentration, you will have a corresponding value of capillary number. This capillary number is simply an indication of the capillary pressure as per the defined equation and defined relationship between capillary number and residual oil saturation. So how to screen, we have another question, how to screen the surfactant. So surfactant as the enhanced oil recovery technique, we have multiple screening criteria for the different surfactant projects. In terms of reservoir parameters, residual oil saturation, reservoir pressure, fluid type, fluid density, fluid viscosity, and so on. So in the literature, we have unlimited number of screening criteria, and additionally, we have most recent technical softwares for screening criteria of enhanced oil recovery techniques. You can you have to define different reservoir rock and fluid properties, and then the software will guide you of the recommended enhanced oil recovery technique in terms of the input parameters. So we have another question: is the concentration values are the same for all surfactants? No, we have. It's based on the project design. So actually, as mentioned in the presentation before starting an EOR project, we have different steps, starting with reservoir characterization and some of screening criteria and lab experiments on core samples to apply or to simulate the effect of surfactant flooding. Then you can make pilot in the on the small scale on the field, and you can define and identify the optimum surfactant concentration using core experiments or a lab experiment based on the core flooding to select the optimum surfactant concentration. So have this been tried on shale gas? No, surfactant in gas reservoir actually we don't. Surfactant actually is not recommended for any gas reservoir because the mechanism of surfactant is to reduce the capillary pressure. Accordingly, you can decrease the capillary trapped residual oil. But in case of gas reservoir, it's not actually the most of gas reservoir we can produce by the volumetric depletion without any external energy to the reservoir like oil reservoir. So the scenario for oil reservoirs is totally different relative to the development of gas reservoirs. So we have another question, say we can use Eclipse 100 for polymer flooding. Yes, I have similar projects to apply to use Eclipse 100 for polymer flooding. Similarly, like the surfactant flooding is it's totally similar to surfactant flooding. You have some modifications in the simulation equations, and then you can define the corresponding Eclipse keywords like the surfactant flooding model. So any other questions? Yes, we have this question as will polymer clog the pores if not flow back? Uh, Actually, I think it means close pores if not flow back. Simply the objective of polymer generally is to control the mobility ratio. That means the polymer will be used to decrease the mobility of water and accordingly increase the mobility of oil and uh, and eliminate or avoid the early water peaks. So polymer is recommended. Actually, I think we are talking about the such techniques, not enhanced oil recovery. But for enhanced oil recovery, the polymer is highly recommended with surfactant flooding to control the mobility of water and avoid early water peaks. Any other questions?
Okay. So I guess that there's no more questions. I want to thank you so much, Engineer Sham, for your time and this really valuable session. And thank you everyone for being with us today. And we hope to see you in our next courses with Engineer Sham and our next webinars also. So thank you again, Engineer Sham, and goodbye.
Thank you so much for all of you and see you in the upcoming events.